This is Dr. Anthony Revis with Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis, Chapter 4, The Use of Polymers. Polymers are used extensively in many applications. Household examples are where we find the use of them in everyday life, and things were very common to us and things we use that we often don't really think about them as being polymers. But if you were to take a look around your home right now, around your classroom, around your job, around most places, you really do see the polymers all around you. You can't escape them. Now, when we consider household examples, there are 12 common polymers that we find in any household, or really office examples will work just as well. Any of your workplaces, if you go around any of the restaurants or any stores, retail stores, or any other places like that, you'll find polymers all over. So when we talk about the household examples here, really you could think beyond the household. Okay? So 12 common polymers are found in the household, and that's a take-home point, and that's something you want to know. There's about 12 common polymers, and these take up a lot of the applications for things that you just normally see in and around you. Okay? So, one is low-density polyethylene. Again, it is low-density by design, and we'll talk a little bit more about what it means to be low-density. Okay? But basically, that is one form. Then we have the high-density polypropylene, and you have to know that these are different. You have low-density, you have high-density polypropylene polymers, and they have different application areas. Then you just have the polypropylene that is just your generic material, everyday, low cost, low manufacturing costs, low cost to the customer type of polypropylene for a lot of general applications, which tend to be a little bit different from being those that have more specificity to them. Polyvinyl chloride is another one. PVC, you know, and you'll learn more about what it looks like. We've already looked at how to do polymerizations, and you'll learn a little bit more about what these look like. Then we have polystyrene, of course. A lot of people are familiar with polystyrene, styrofoam cups and things of that nature. Teflon, Orlon, PVC, copolymer with saran, which is basically saran wrap. No surprise there. PVA, which is used in the white glues. And then we have nylon, nylon 6, and nylon 666, which is used in carpet, and depends on the type of carpet, whether it's very expensive, low expense, or shag or non-shag. Depending on the application, you'll use a certain weave for a certain polymer and weave it for the carpet. Then you have the polyurethane families of materials, and then you have things like PMMA and which is plexiglass, methyl methacrylate. So these are acrylate polymers that have been polymerized. So these are the 12 common ones, and as you go through the rest of this particular course, you'll be more familiar with where they are. So I encourage you to actually look around your home, and you'll see examples of each of these. So now, industrial polymer science focuses on the commercial application. And when you talk about commercial application, the bottom line is, where can you sell it? Where can you make money using it? Okay? All right? So that's very, very important when we think about it for the industrial polymer science. So you want to make a product. The emphasis is on research and preparation of these as a scientist, and preparation for some industrial application. So the industrial polymer scientist doesn't think as much about creating and understanding new fundamentals. The industrial polymer scientists, most of them, think about how to take those fundamentals and move them forward. Now, there are some who spend their entire careers looking at just the basic fundamentals of it, the physical properties, understand how to measure them, how to manipulate them, and how to get the functionality to have certain interactions, and that's very important. But the majority of the polymer scientists and we'll look at how to move that forward to a finished product. Okay, so industrial polymer scientists adopt a business outlook and understand the commercial applications on the marketplace for the polymers they are developing. They know which market they're going to put these in, and that's why they are working on them and spend their time in the laboratories. These scientists also consider the needs of the marketplace they're serving. So, which marketplace am I serving? Am I serving entertainment? Am I serving healthcare, beauty, construction, automotive, electrical, etc., etc.? Okay, do I need this to have a certain mechanical property, a certain look? And do I need to be able to color it? Do I want it crystal clear? These are types of things that cross the minds of the scientists working. What's the end use have to look like, feel like? How does the customer experience it? And how do I manipulate the science and the polymer backbones to give me that? And it's a fun thing to do, to figure those types of things out. They develop products that meet specific customer needs. Is it going to be a toy? Is it going to be a basket? Is it going to be a mat? Is it going to be some film? What is it going to look like? So that's what you look at. And again, the polymer chemists have thought through these things, and as it turns out, there are 12 common polymers found in a household that they figured out that meets a lot of the demand for household products, and not just household, but again, for office spaces and things of places like that. Okay? So now, let's take a look at the leader of the pack, if you will. That leader tends to be polyolefins, and in this case, polypropylene. Polypropylene is polymerized from propylene monomer, a 3-carbon atom that contains a double bond. Or, if you consider it from the polymerization perspective, you have a double bond to which a methyl group is attached. The double bond is what allows you to build a backbone. The methyl group is what allows the properties along the backbone the features along the backbone to be developed for certain properties. So you want to develop these features along the backbone that comes from the methyl group, and that's what gives you the properties in the finished polypropylene polymer. So we kind of look at 3 different varieties, if you will, of the polypropylene. You have the plastic sheets, which is an Atactic polymer. An Atactic, we now know, means that there's a random distribution of the methyl groups. And this is usually your low-income types of applications, and just plastic sheets is a big area where they're used. So if you see these plastic sheets that construction workers like to use to put over things, to cover things while they're waiting, or something of that nature, that's probably just a regular polypropylene made from a radical polymerization process to make the Atactic polymer, which is just used for general purpose applications. Then you might have a Syneotactic, and in the case of a Syneotactic application, it's made using what's called a Ziegler-Natta catalyst. Okay, and when you think of the Ziegler-Natta catalyst, there are several varieties of them. But for the Syneotactic polymer, typically there's a vanadium catalyst that's used for it. So it's a vanadium catalyst, or that's used typically with a co-catalyst that has an aluminum metal in it, and this gives you this stereospecific polymer where they interact with the metal surface on one side to form a complex. Complex is the word I'm looking for. Forms a complex with the metal. Okay, that complex undergoes insertion, and then another olefin comes in and complexes, and it inserts, and through that alternating insertion, we get the Syneotactic structure. Syneotactic structures is found in things like toothbrushes and other hard devices like this. So you find them in these hard items, things that make plastic handle type things. Tend to be Syneotactic, have Syneotactic structures. And again, these are made by Ziegler-Natta catalysts. Typically, a vanadium is the one that's used for this. Then you have the isotactic. Isotactic is also made using a Ziegler-Natta catalyst, but it tends to be titanium with an aluminum, and as you now know, Ziegler-Natta catalysts also use solvents, product solvents, water or alcohols to help activate the catalyst complex. And so when the olefins complex with that metal on a stereospecific face of that metal, when it undergoes complex insertion, it does it such that the methyl groups all align on one side. And this gives you a completely different polymer with different physical properties. Each of these three have different physical properties because of how the methyl group is oriented on the backbone of the polymer. And isotactic, you might find some isotactics in furniture. Plastic furniture would be an example of that. And you need plastic furniture to be a little bit tougher, and you also need certain other stretch properties in it. And the isotactic structure affords you those types of features, and that's why they're chosen to produce polypropylene. So again, you have polypropylene polymer made by the atactic process, usually a radical process with a radical initiator such as benzoyl peroxide, or AIBN would be a carbon-based radical. Then you have the syneotactic, which has the alternating methyl groups, polypropylene, which is made by vanadium catalyst. And then you have the isotactic, which is made by titanium catalyst. Again, most of these Ziegler-Nattas are co-catalysts with an activator. And because of their physical features, we get certain basic physical and mechanical properties. So let's take a look then at a low density polyethylene, okay, which would be different from just your traditional polypropylene or the other polypropylenes. In fact, you might have a low density that's used for similar applications, same applications. It's all application focused, by the way. At the end of the day, if it meets the purpose, it's the right polymer. Okay, that's how commercial chemists think, and polymer chemists. Did it work? Yes. If it worked, that was the right polymer. Okay. So if you take a look at low density polyethylene, then if we talk about it, okay, low density polyethylene is made with a catalyst, takes ethylene and polymerizes it, okay, and we take these catalysts, and you would get the low density polyethylene. And these catalysts can be any of the regular catalysts that we talked about, any of the radical polymerization catalysts or the Ziegler-Natta catalyst. It really just depends on how you want to run the process. But more times than not, when you see branching, and if the branching is self-induced or induced during the process, that's usually through a radical type of process or radical chemistry. So here this might be an example. Low density polyethylene, for example, might use and typically will use a common radical catalyst because it initiates certain branches. And the polymer chemists have, through understanding this mechanism and the principles involved in initiation, propagation, and termination, when we think about the kinetics of those, you can pretty much predict how many branches you want to get. And most of this is now software driven or app driven, whereby it's pretty well known that if you run it with this catalyst under these conditions, you'll get X amount of branching. You run it with this one, you'll get Y amount of branching. And all of that is really well worked out and something that might be discussed more in a more in-depth look at it. So for now, understand that if you take ethylene and you polymerize it with a radical, you're very likely going to get you will get your low density polyethylene, and it will have branch points in it. That's what makes it low density. What makes it low density is the branch points, and we'll talk more about that as we go throughout this course. But low density occurs when there are branches. The branches interfere with close intermolecular interactions of the different polymer chains. So where these polymer chains have less interaction, chain-to-chain interaction, then it's low density. Okay, so low density occurs when the polymer chains are not physically close enough or in close enough contact to allow for more intimacy across the chains. So less intimacy, less contact occurs because of branching. Therefore, we get lower density. In other words, said simply, if you put it simply, it means it doesn't pack as well. Okay, when it doesn't pack as well, it's low density. In other words, the chairs in the kindergarten don't stack well. Okay, all right, and that gives you low density. On the other hand, you have high density, which means it's more specific. More specificity very likely means, and does mean, by the way, that you have the Ziegler-Natta catalyst that you're using. And now, since you have the Ziegler-Natta catalyst that you're using, you can expect more specificity. More specificity leads to closer packing of the chains. Okay? That gives you the high density. In other words, you can stack in more chairs in the kindergarten classroom. Okay, because all the chairs are the same. You stack them together, they stack really neat, and it works. So here you have these polymer chains that interact like that. They interact really in close contact in an ordered stacking fashion, and this gives you a higher density. In other words, more polymers per that particular area, or more grams or more mass, right, per volume. Okay, you get it? So per volume you have more mass, and that's because you can pack in more of the polymer chains. So HDPE is produced using Ziegler-Natta catalyst, very specific, and that way you get less branching. Remember, radicals produce branching. Ziegler-Natta catalysts typically do not produce branching. And so when you want no branching and you want high specificity, that means Ziegler-Natta. In the case of polyethylene, this polyolefin produces the HDPE with the Ziegler-Natta. Applications. Some of the low density will be toys, perhaps maybe not this exact toy in the diagram, but many of the toys and parts of these toys will be in there for the low density polyethylene, relatively inexpensive toys that are not going to get roughed up and scuffed up too bad and tossed around. But in fact, some of them are too. But then you have the buckets, the pails that you use, the plastic buckets. Many of those will be high density polyethylene and others such as this. But you can Google and find many of the applications for these. So these are just examples. So to recap, low density polyethylene is prepared from ethylene using a radical catalyst with branching. The branching doesn't allow intimate contact of the chains. Therefore, the density is lower, less mass per volume. If we use a Ziegler-Natta catalyst, we would then get a higher degree of specificity, more uniformity, therefore allowing for more intimate packing and contact to give us the HDPE. Now we've talked about these polymers and this idea of atactic, syntactic, and isotactic. Let's talk further about that in terms of the types of properties that you see, which helps you develop products that customers like to pay money for, like to buy. Okay, so when we look at these catalysts, excuse me, I'm sorry. When we look at these polymers, again we have the atactic polymer, the syntactic, and the isotactic. The atactic being produced primarily by radical processes. There may be some forms of Ziegler-Natta that are not quite as specific and might give you a similar type of random, but for the most part, Ziegler-Nattas are well-defined, give you well-defined structures, which is why they're used for syntactic and isotactic. Okay, And again, Atactic, one of the ones that's used a lot for Atactic is a vanadium, and the one for Atactic is a titanium. And so if you take a look at the difference in terms of the properties, and this is what allows them to be used or why they are preferred for certain commercial applications. So when we think about why materials are preferred for certain applications, these are three of the features that are looked for or discussed in these polymers. In the first case, Atactic tends to be amorphous. It's non-crystalline. There's no crystallinity in there. And there, since it's amorphous and no crystallinity, it has more of a glass transitioning than a true, very sharp melting point. Okay, and its density is the lowest of the forms. Okay, and you might expect that again. We've talked about that's why it's called low. It's used for low density applications, and then for lower density, applications. Then you have the mid-range with some crystallinity, the Atactic, because there's more order in it, which means the polymer chains will have more intimacy. Therefore, note the TG is down to minus 8 degrees C now. Okay, and so the melting is a lot higher, 160 degrees, as opposed to the melting again for the Atactic at 110. But there's really not a true melting point for Atactic. It's really a glass transitioning. But we basically identify a melting point there, but it's a bit broader. It's one thing. It's the point we really want to emphasize there, that it's broader. In terms of the high crystallinity one, that's the isotactic. And there's about up to 60% crystallinity in this form, and which means the TG is now lower, and the T melting is higher, so you get a wider spread there. Okay, and it gives you, when you get about 85-90% isotactic, this is what you expect to get a higher density at about almost 1 in terms of density, less than water, which means it still floats. It's a plastic that floats on the water. Okay, so this is what's being manipulated when we carry out these processes, and when we run these reactions, we're manipulating these features. How much crystallinity is in the polymer? That helps to define which applications it might be useful for. What is the density of the polymer? That helps to define the application for it. And what's the TG? What's the TM of this? That helps to define the application. How much temperature can it take, and in which temperature applications might it have utility? Okay? So, if we look at that and think about it a little bit further, then we note then that Atactic polypropylene is useful as a solid construction material. So for construction type materials, it's what you use. It is used as an adhesive additive to soften matrix materials. In other words, if you need to put something in to act to help soften it, oftentimes they'll grind up the Atactic PP, put it in the blend, and you get softening of these hard materials, these hard matrices, these hard materials, and they help soften it. But at the same time, because of its solid material, okay, and because it is a solid material and can be compounded in, it helps to soften the other material. Okay. The isotactic polypropylene is a high melting solid. Can be molded in a machine into structural components. In other words, you can take isotactic and you can shave it up and make parts out of it, or make designs and things of that nature. You can't do that. Atactic won't allow you to do that because it likes the stiffness or the crystallinity. Polypropylene can also be made translucent, but is not as readily made transparent as polystyrene, acrylic, or other plastics. So for the most part, when you want something pretty with shine and see-through, it's not polypropylene you're going to use. You're going to go to an acrylic or polystyrene, which is used in CD cases, or a lot of the high-end stores will use polystyrene and acrylics for that wow look when you go into the high-end stores. They'll have that beautiful display, and it'll be an acrylic or polystyrene. Okay, it won't be polypropylene. Polypropylene will be in the lower-end stores. Okay, it is often opaque. Polypropylene, that is often opaque, or it can be colored if you add pigments to it. So these are the properties that we look at. Okay, so we've taken you through, taking a look at these polyolefins. Okay, we compare polypropylene, which we're talking about now, in its atactic, synotactic, and isotactic forms, and we compared that to polyethylene. Okay, which comes in a low density polyethylene or a high density polypropylene. And again, we look at these properties of these. Is it amorphous? Is it crystalline? Is it high crystalline? What's the density? Low, medium, high densities. What's the TG? What's the TM of these polymers? Really helps us to get a handle on how they might be used. So let's look at another example here of a comparison here between polypropylene and polymethylmethacrylate. Would be an acrylate, which gives you this crystal clear kind of polymer. Also, just as a note, acrylates are also used in radiation cure coatings as well on floors and things of that nature. All right, so now again we have this atactic polymer, right? And we now know what atactic means. We understand how atactic polymers are used, okay? And we know about these synotactic and isotactic polymers. So let's compare those groups across two polymers, just to show you the difference that the backbone and the chemistry and the features can make. If you take polypropylene and you look at the values here, here we're just showing you the TG of each of these. Just to show you an example, you start with a TG of -20 up to 0 for the polypropylene. But in terms of polymethacrylate, its TG glass transitioning doesn't occur to 100 degrees C. For the atactic, 120 degrees and 130 degrees. So you might guess that one might be using an application where the temperature, where higher temperatures are going to be reached and going to be seen. So this is why, the plastics, right? When your car, the plastic seats in your cars. Yep, you go out, you sit in the car, and it gets really hot. That's because it's undergoing, it's reaching its TG, okay, and unlike PMMA, it's going to take a little bit before it'll really get warmed up there. Okay, so it won't reach until 100 degrees C, unlike your plastics. Might start to melt a little bit, or get a little hot when you get a little warm out in your vehicle. Okay, so all of this goes into it, and they think about this, where they're going to use it. Isotacticity, by the way, is measured in boiling hexane. So boiling hexane, and they use those values in terms of how long it takes and etc. to determine its properties. Okay, so that's how it's done. And here's what you want to know: the higher the isotacticity, the greater the crystallinity, and thus the higher the softening point. As a higher softening point, again, your cars in the hot summer. In a vehicle, start to soften a little bit. But if it has more crystallinity in it, okay, that means it's going to be more rigid, and it's going to also have what's called a higher E modulus, which means it's less elastic. So when you think of E modulus, you think of how elastic is it. Higher E modulus means it's less elastic. Low E modulus means it's more elastic. Okay. And the higher the E modulus, the greater its hardness. Okay, so you want to be aware of those. And so these are the types of properties that we are aware of and that we examine when we are involved in polymer science. So let's do the same thing. Let's compare a few features of low density polyethylene with high density polyethylene. So just to compare a few more of these features. We won't read this table in full detail, but we just want to make you aware that it is here and that it's available. And if you just take a look at a few features here, you'll notice that the intermolecular forces branching is strong, less branching in HDPE, and stronger intermolecular forces, the opposite with LDPE. You notice that the density of LDPE is typically less than that of HDPE. The applications tend to be in different areas. Some LDPE will be water bottles, but many of your soft drink bottles today, the soft drink bottles in particular, are usually PETE. Some of the water bottles will just be plain plastic. We would say plain plastic, I apologize, low density polyethylene. And you'll have HDPE for things that oil tanks and things of that nature that require a little bit more toughness and are more solvent resistant. You'll need low density where it's more ductile. You don't quite need it to be as ductile. Just need to be a little tougher when it comes to HD. And the production is radical polymerization. And for HDPE, you use a catalyst, like you'll have what's called metallocene or chromium. These various transition catalysts might be used in HDPE, and in some cases might even use a Ziegler-Natta, which some of these tend to fall into that category as well. So be aware that it's very specific catalyst, more sophisticated, if you will, catalyst. The flexibility, LDPE is less flexible, and DPE is less flexible. Let me say that again to be sure I said it. LDPE is very flexible. HDPE is not very flexible. Okay, that is a major differentiating factor for these two polymers. Another example of an olefin polymer would be shown here as PVC. In the case of PVC, which is polyvinyl chloride, you get it? It's a vinyl, starts with a vinyl chloride, which is ethylene chloride, okay, and is polymerized. And if you form the atactic polymer, you've already guessed it. It uses a radical initiator for the atactic polymer, and because of the chlorine functionality, this material gives you the toughness and rigidity that you need even in this atactic amorphous material. And this is used for tough areas like plumbing pipes that you don't see them, and then they're also used in many of the shoes, the plastic shoes, synthetic shoes. They're used quite a bit for that as well, and several other applications. Shower curtains tend to be PVC. Some aren't anymore. Some are moving away from PVC because of the chlorine. They don't want the chlorine in the product. But they're used for applications such as those. So PVC, and that's why sometimes you get the plastic curtains, and they have this bit of an aroma. That aroma is that pipe smell. Okay, that is that aroma. Okay, of that particular polymer, and so you get the atactic PVC. What about some other examples of olefin polymers? Okay, so let's transform some other olefins into polymers. If we take tetrafluoroethylene and we polymerize it, we will get Teflon, PTFE. which is used quite a bit in cookware. A lot of your tough bakeware and materials of that is also using gears where you want to get slip as well. So that would give you Teflon. The other polymer you might get, if you take acrylonitrile, you might get Orlon. And Orlon's used a lot in textile industry for various types of textiles. And you get this polymer that's made. Another one we've talked about MMA, PMMA. Here we've talked about already, but let's just reiterate it again here. You take PMMA and you get the polymethylmethacrylate shown here, which is used for protective materials, shields and things of that nature. You see these a lot. You'll hear the term plexiglass or lexane glass, those types of glass. That's where you will see them. Used. So they use a lot in face shields and other types of shields where you basically need to block the impact of an object against it. Then, if you take the example of a copolymer of vinyl chloride and vanillidine chloride and vinyl chloride, and you polymerize them as a copolymer, you get Saran. This product's made very popular by the Dow company. So Saran has a lot of applications, including used a lot for packaging, not just sandwiches and sandwich wraps, but just packaging in general because it stretches. They wrap it around a lot of things. You see it a lot in shipping places where they'll have these big rolls of Saran and they'll take them out and they'll roll it around everything and it's ready to go. It has this really nice clean property, and that's what revolutionized the industry. But you can also make it where it doesn't have that clean, that real tough, that real strong clean. So it's really an example of where you can manipulate the chemistry to make everything from really fun cling to not so much cling in terms of the Saran wrap. And that's all based upon the monomer distribution. And when you use certain types of monomer distributions, we have to adjust the catalyst and the process to accommodate the output. And that output, by the way, is based upon the in-use product. One of the important features that helps a polymer create some of its features or unique features is whether or not it polymerizes in a particular fashion. Polymers may polymerize in a head to tail, which is perhaps the most preferred fashion in which they polymerize. Most of the examples that I have been teaching and showing in this particular class involve head to tail polymerization, meaning that the front of the polymer attacks the back. The front of the monomer attacks the back of the adding monomer to give you a head to tail. However, you might also have head to head, meaning the two monomers would meet, both of which would meet at their head, and their tails would be pointing out, and then you would have a tail to tail. Okay, so you have head to tail, which is by far and large the preferred way that these polymers will add or polymerize, and then you have the head to head. What defines a head and tail is where the radical starts, by the way. Okay? The point at which the radical starts is defined as its head. Okay? Now, there's also a random polymer that can occur as well, in which you have a combination of, you don't know what is head to tail, you have head to tail to tail, and any other combination thereof. So you can also have this in a random fashion as well. Depending on how it does that, it will give you a certain property, a certain output. Many and most of the processes that are discussed and are found for many of the major commercial applications involve head-to-tail polymerizations. However, there is a lot of space still there for the other types of polymers. Okay? So you want to keep that in mind when you think about it. And how they polymerize, again, will influence their properties. The properties will then be used to design in-use products. Another example is to polymerize vinyl acetate to make PVA or PVAC also, which is the acetate bound alcohol, which is then further derivatized to the final PVA that's used in most of the white glues, the Elmer glues. This is your Elmer glue formulation here. So you basically take VVA, it's a PVA glue. Okay, so you take the vinyl acetate, and the reason you take the acetate is because it is stable in the what's called the enolate form. So let's repeat that to make sure we said it clear enough. PVA, pyrrole vinyl alcohol, is made from the vinyl acetate olefin. It has an acetate group on it to hold it in the enol form. Therefore, we have a pi system of double bond to polymerize. Once it's polymerized, the acetate is removed. Essentially, the equilibrium for vinyl alcohol lies to the side of the acetaldehyde, and that's what's very important about it. So this is a way of manipulating other types of organic chemistry structures or organic reaction chemistries to achieve your final goal. All right. So that's it for your white glue. Another form of polymerization is actually one that involves a self-condensation. The self-condensation of ring open caprolactam produces nylon 6, which is a homopolymer. So essentially you take the ring structure, which has the amide group in it, and you polymerize it under acidic conditions. Okay, you carry out the polymerization and you form the nylon 6. Now, when we say acid conditions, it's actually fairly mild conditions. Really, it's really an aqueous polymerization that uses water in the mechanism. This is a really strong acid solution. It's basically it polymerizes it, whereby the water is added and the ring opens, and it continues to open, transferring, and there you have it. Okay. Now, another way to make a nylon material by condensation, okay, is by self-condensation, is by using a copolymer of hexamethylene diamine and adipic acid adipic acid. Okay, and when we carry out that reaction, you would simply add the materials and you form the polypeptide bond, the peptide bond or the amide bond in this material. So again, let me recap. Basically, you can do self-condensation, and really on the mild conditions, you can get the ring to open to form the homopolymer, or you can carry it out where you add the two comonomers to produce the copolymer, which is nylon 6,6, and they both have very good uses in the marketplace. Okay. Polyurethanes, another example of a condensation polymer, and it's a condensation between the isocyanate and the ethylene glycol. They're both difunctional monomers, so both these difunctional monomers find each other, they condense. Condensation means you're going to have water, and so keep that in mind. I should have mentioned that. When you see condensation, that means you're going to produce water, okay? And so when you make the nylon 6 or the nylon 6,6, you produce water because it's condensation, either self-condensation or the co-polymerization of the two co-monomers to make the copolymer, or back to our polyurethane, you basically, this isocyanate and the ethylene glycol, they go together, and once they go together, we get the copolymer polyurethane, which is used for padding and insulation. It's one of the big uses of it, where there's padding to go on or where there's insulation. Polyurethane usually wins the game, and it's used extensively there in the industry. Okay. Another particularly useful thermoplastic polymer is polycarbonate, and it has lots of applications in the industry. An example would be uses in CD cases and DVD cases, the hard plastic cases. The polycarbonate is formed as a copolymer of bisphenol A with phosgene catalyzed by sodium hydroxide. So it's essentially a base catalyzed coupling that, if you looked at the polymer, it appears to be a condensation. And by the way, there is a process for preparing polycarbonate by condensation, but the major manufacturing process involves the one shown here in this slide, bisphenol A with phosgene. And just take a quick look at the properties of the polycarbonate that makes it particularly useful. It's, again, its tensile strength is pretty good. If you compare that tensile strength with that of natural rubber, as we show you in the 2 bullet points in this slide, it compares really well. It's pretty tough material. The tensile modulus is 2.4. Elongation is only 110%. And compare that with natural rubber, you see that it really does not elongate at all. So basically, these are some good properties to have in this material, and these properties make polycarbonate particularly useful. We will talk more about properties and how we determine the performance of many of these polymers a bit later in this course. Now we talk about these co-monomers. Okay, then let's show you a few examples here then, and talk about a few other copolymers that have commercial application. Again, this class is concepts in polymer chemistry, so it talks a lot about where the products are used. So let's talk about this copolymers. Copolymerization of equal molar mixtures of different monomers typically gives statistical copolymers. So you get basically 1-to-1. It's the real bottom line. It's what we're saying. So you add 1 unit of A, 1 unit of B, you're going to get a polymer with 1 unit of A, 1 unit of B. If one monomer, however, is much more reactive, okay, a nearly homopolymer of that monomer can be formed. So that is actually used as a trick. Understanding the rate that these like to condense is used as a trick in order to get certain distributions of A and B monomers in the product. Okay? So here are some examples of some polymers that are used, copolymers that are used a lot around the household, or actually just out in the world, frankly. So we'll take a look at the A. We'll have a vinyl chloride, and B is a dichloro olefin, with the dichloros being on the same carbon. That's used to make saran, which is SBR. and it's used for films and fibers. And that product is made really popular by Dow. It's a Dow invention. The next one we show you an example of, if you take butadiene and you take a styrene monomer, the styrene monomer. So it gets styrene butadiene rubber, which is used in tires. And this has huge application, again, in the automotive industry. Okay? Right? Goodyear's a leader in that. Then you could take butadiene and a nitrile, a vinyl nitrile compound, and copolymerize it to make nitrile rubber. And adhesives and hoses are used a lot for this polymer is used a lot for adhesive and hoses. Would be strong application for those. And then you could take a combination of fluoro materials or chloro materials and make these really oil-resistant gaskets and inner tubes, things that are used for areas where it's going to see harsh conditions. And so you make this butyl rubber or Viton. And so this is used in these areas where it's really harsh conditions, and you really need a material to last a long time, but have the flexibility and the other properties of a rubber. So you want the toughness, you want the corrosion resistance, things of that nature. Not completely corrosive resistant, but enough for the application. And so you want those kinds of features. You basically polymerize them in. So copolymerization is a process of allowing polymer scientists to mix the properties, the features of one polymerized monomer with the features of another polymerized monomer into one new product with new features and for very specific and new and unique applications. That is the beauty of copolymerization. Oftentimes when the chemists can't achieve it in one monomer, they will look for solutions by doing copolymerization. Okay, and making the product, the stability of it are just typically are stable as the mono polymers are. Okay, as the homopolymers are using a single monomer. Okay, so they'll be just as stable. And so these are the features we get from copolymerization. All right, well, that brings us to the end of this chapter. So let's recap a few important things that we want to remember from chapter 4, the use of polymers. We want to remember that there's about 12 polymers that are used, and you want to be familiar with those. And the leader, frankly, is the propylene. The polypropylenes tend to lead the pack here. And then you have various forms of the ethylenes, the low-density polyethylene and the high-density polyethylene. You have the Teflons, the polystyrenes. You have the Orlons, the Cerans, the PVAs, nylon 6, nylon 6,6, and you have the polyurethanes, as well as the plexiglass, which are polymethylmethacrylates. And these are the polymers that industrial chemists spend their time working on. Features of the polymer are very important. Those features start with the features of the monomer. If the monomer has a side chain, that side chain can show up as an atactic form, which tends to be more flexible and lower density plastics and used for sheets. It can also show where there's alternating groups, which is a slightly higher density than the atactic, which would be for things where you want a little bit of toughness, a little stiffness in it. And then the isotactic would be for those things where you want more of a crystalline format, where it's a higher density for high density type applications. And some of those high density applications will be as simple as a bucket. Some of the low density application will be as simple as a kid's toy. Because of the orientation of the atactic, syntactic, and isotactic groups, we have a difference in terms of crystallinity and TG and T melt. And that TG melt will follow from atactic through to isotactic with increase in terms of its TG. Okay, and that's not only for polypropylene, that's also for other polymers as well. Like for example, polymethylmethacrylate has much higher TG than polypropylene, but it follows the same trend depending on whether it's atactic, syndiotactic, or isotactic. Okay. Then we have the different applications of each of these unique polymers. We have these unique applications of also the copolymers as well. And there you have it. That completes Chapter 5, Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis.